introduce Isabel Dotti, who's here from Universidad Nacional de Cordoba in Argentina, and she'll be talking to us about Killing-Yano tensors on Homogeneous Manifolds. So thank you very much.
Thank you very much. Okay. Thank you very much to the organizing committee for the possibility of being here. Congratulations, Adolfo. And I think everybody knows that I am very happy to be here in Mexico. Okay. So we start with this is a fancy name, but I mean, you will see that it's a natural generalization. Okay, we will be working with a Riemannian manifold. So we have a metric, and we denote by that symbol the Levi-Civita connection. And the notion of a Killing vector field, okay, is in this way. I wrote in this way. So it's Q-symmetric in the in the second variable, the derivative. And for the dual one form. If one take the dual one form, then look at the equation, the second number 2. The dual one form satisfies this relation for any vector fields xz that interchange the variables. It's Q. One form that satisfies this condition is known as a Killing one form. So it's the dual of a Killing vector field. Okay. So we will see that the Killing-Yano forms is just a generalization of a Killing one form. Okay, this is just to review that Killing vector fields is like the infinitesimal version of isometries. The one parameter group associated to Killing vector fields consists of isometries, and the flow preserves the metric. Other much more properties, but some of the main properties is the bracket of 2 Killing vector fields is again a vector field, and the space of Killing vector fields is a Lie algebra, and it measures the symmetry in some sense of the manifold, of the Riemannian, okay, with the metric. So this is just some properties, is not. Okay, this result, due to Bochner, shows that, I mean, not every Riemannian manifold carries Killing vector fields. Okay, if one has a compact Riemannian manifold with negative Ricci curvature, then zero is the only Killing vector field. And this is just by evaluating. So, I mean, it's something that that one search for. This is related to isometries. So, for example, in this case, we'll say that the isometry group is finite. in this case, for that metric. Okay, this is just look at equation 3. So in 52, Yano considered the generalization of Killing-1 forms to orders Killing tensors or forms of order P. It's just the same equation. Okay? The same equation, but interchange is Q in the first variable, say. So this condition, equation 3, is equivalent to the derivative of the form to be like I don't remember how was called the interior multiplication times the derivative. So it's a relation between the Levi-Civita derivative or the derivative and the differential. So this is this 4 is the equivalent of the Killing-Yano equation. One says that a P form satisfies the Killing-Yano equation if it satisfies equation 4. Okay, so it's a relation between one derivative and another derivatives. Okay, so in the case of one form, this is just the Killing-1 form. So it's nothing but the generalization of the Killing-1 form. Okay. Okay, there were some observations and from this kind of forms, of satisfying these forms. And so from the definition, I mean, like most articles started in the most articles are in the physics literature for many years. No, not many applications. Yeah, application, but not a systematic study. Okay, so this is okay. Some general results. The general results, I am quoting some, is Moroyanus, Selmeman, Belgum have worked on. And they take a specific, for example, the first result says that if you want to take a Riemannian, a quaternionic Kähler manifold and Killing P form, okay, you fix the Riemannian with these extra properties, okay, that is extra condition, quaternionic Kähler, then the forms are parallel. Okay, see that if one takes a parallel form, this is 0. Okay, and the derivative of the differential of a parallel forms is also 0. So parallels are something like the trivial solutions of this equation, parallel forms. Okay, so this kind of results, the first two are something like answer some question about some Riemannian manifolds where the metric is fixed and known, and the last result is like Papadopoulos in 2008, for example, studies just specific forms, consider specific forms related to G structures, okay, and to see if they are satisfy the equation or not. And the answer is that mainly they are, they have to be parallel. We don't, those forms are not like non-trivial solutions. Just to. So what I will now say is what happened in the case of two forms that satisfies this equation. Only two forms. Okay, in the case of two form, to see, I mean, we are starting. One form, the generalization to P form, and now what happened in two forms? If you want to consider two forms, then the equation is, I mean, it doesn't have a number, but it's that equation. Where T, what is T? Is the associated. We have a Riemannian manifold, and we have a two form, and so this is the endomorphism relating, okay. Okay, in two forms, this equation is equivalent to the other equation that is down. Okay. Good. This equation. Okay, so one may consider this kind of triples like a manifold. You will see now that this looks like an, oh, sorry. I think I will say it like this. Okay, you take a Riemannian manifold and an endomorphism of the tangent and consider the two form, the associated two form. This will be just taken, or the two form or the endomorphism. And the condition of satisfy the Killing-Yano equation is exactly this condition. Okay, ahí está, this condition. Okay. Okay, this is, okay, this is the particular case. So, you see where I am heading. Just to show that if you want to take an almost Hermitian manifold, take the associated two form, that is the Kähler form, or in general. Then, in this case, Killing-Yano two forms is equivalent to the manifold to be Nearly Kähler. So, Killing-Yano is nothing but, I mean, a generalization in the case of two forms of Nearly Kähler. What is a Nearly Kähler? Okay. Nearly Kähler is just this condition exactly. Oh. Okay. Kähler. Now this is J is parallel. Huh? Okay, this is J is parallel. Huh? And Nearly Kähler, this is a okay. So what we were saying previously is that we are taking M to have it. It's just to consider this kind of manifolds where T is skew. Okay, and so this is kind of, this is the same as the Killing-Yano equation in the case of two forms. Okay, this is what we are going to. Nothing but that. Okay, so here is Joe, Alfred Gray, studied a lot, I mean, about the homogeneous spaces, the references I can give about the homogeneously group defined by the group automorphism, and they both a conjecture that an homogeneous manifold carries a univariate metric. That's almost Hermitian. I mean, if one asks this endomorphism to square to be minus the identity, and then will be almost Hermitian, okay? And carries a structure that is nearly Kähler, but not Kähler, I mean, satisfies this equation, and is not parallel, not trivial, the solution in the sense of the equation. No? If and only if one has a condition on the I don't know, I wrote H. Okay. That means K. Okay, well, I think, I mean, this was solved, gives a positive answer to their conjecture in 2005. Okay, now, trying to search for solutions, I mean, solutions on metric, I mean, Riemannian manifolds carrying this kind of forms, of two forms, we started, I mean, working on Lie groups with skew endomorphism, metric Lie groups with the skew endomorphism, satisfying this equation. Okay, and obtain a condition at the Lie algebra level. A condition at the Lie algebra level, and obtained some metric, some Riemannian manifolds where all the invariants, I mean, in the previous talk they were talking about left-invariant metrics, okay, left-invariant metrics, but even left-invariant metrics carrying this kind of two forms, associated two forms. So even we had this algebraic condition is not that easy to obtain manifolds, to obtain solutions. But the first one we obtained it with colleagues is that, okay, we cannot search for this kind of solution in the Heisenberg group, in the real Heisenberg, but the complex Heisenberg, the six-dimensional complex Heisenberg, I mean the realification of the complex Heisenberg, it does have non-trivial solutions to this equation. Not only it has a non-trivial solution to this equation, but moreover, it doesn't have a nearly Kähler structures. So these are, like, in a sense, are pure solutions. So this is what is called there the Wasawa manifold, is exactly this Lie group divided by the integers lattice. So to obtain compact examples. This is nothing but what is said there as the Wasawa manifold is nothing but n divided by a lattice. So this, we have okay, this is something that we work with a colleague also. All the results are done with some colleagues at Cordoba. That this is like a technical result that is, but the main thing is the main consequence is, for example, what is written here. In particular, this holds for any inner product on a non-abelian nilpotent Lie algebra. It means the solutions on nilpotent algebras, the invariant solutions on nilpotent algebras, if one takes, that's why we search it in nilpotent, because the invariant solutions will not be parallel, will be pure solutions. No? I mean, if a Lie algebra has an inner product such that the intersection, there are no skew-symmetric invertible parallel. Okay, parallel. So if we find solutions, will not be parallel, will be non-trivial. No? Because, yes, there are more solutions that cannot be, exactly. I mean, this is in the case, yes. Hmm? Yes, this is, I mean, this result is in this case, but there are some situations, I mean, I don't know what happens when, for example, the center is, like in the nilpotent case, I can split the group, but if the group is not, I don't know. So this is, I mean, we were searching for solutions that not parallel, and this, so what I showed previously about the complex Heisenberg, also, I mean, what happened in the complex Heisenberg can be generalized and have others nilpotent Lie groups with a non-trivial solution. I mean, it's not the only family obtained. Okay, now a student of mine now is working on, I mean, she's working in the case of, I mean, of what happened in the case of full flag manifold, to see what are the, if one can obtain solutions, non-trivial solutions. So she's working on that, and I mean, the main, I mean, the first condition she obtained is something of the sort, okay, this is, the V has to do with the coefficient of the tensor. I call E now, she calls E, the endomorphism. Here is, so now in here, E is what previously I called T. I mean, it's an endomorphism of Q. Since we are in Planck manifolds and invariant, this will be like a series for each root space. On each root space, we have a series of number, V alpha 1, V alpha 2, V alpha. Okay. Okay? This corresponds to the transformation. This corresponds to each root space at the complex level, and then, I mean, is lambda. This corresponds to the metric, the invariant metric, okay? So, in terms of this U plus, she's trying to determine when the tensor is parallel, when the tensor is codicy, when the tensor different properties for tensors at in the full flags. So she's okay, these are, I don't know. Okay, it seems, I mean, in the case of when the group is SL3C, okay, she can determine all type of solutions. It is known that in that case there are nearly Kähler solutions, Kähler solution, nearly Kähler solutions. what is Kähler solution, nearly Kähler solutions means, okay? That in this case, Kähler or nearly Kähler, here I have plus or minus 1, plus or minus 1, plus or minus 1, okay, the number, because to the square, this is all multiplied by I. To the square has to give me minus 1, okay? And so this is like a series of imaginary numbers. And these are the coefficients of the metric, okay? So in this case, SL3C, it seems, I mean, can be solved completely. And it's known that for other groups in the full flux, is the only case where we can have a nearly Kähler. Full flux, only in this case we can have a nearly Kähler. The other, but it seems that she found, I mean, solutions to the Killing-Yano equation in other cases. But this is like in progress. Okay, now show like how to obtain a different type of examples to see that you can build a solution to this equation deforming a nearly Kähler solution. Like, for example, if one takes a Riemannian submersion with these properties, okay, that the totally geodesic fibers, but it has the strong restriction that M carries a complex structure, the vertical goes to the vertical, the horizontal to the horizontal, and so one takes a deformation of the metric. I mean, this is like a standard. Then one can consider like these two variables, A and B, and one can find solutions to the Killing-Yano equation in this family of manifolds, okay, but deforming a nearly Kähler, because this case is known that they have a solution to the nearly Kähler equation. Here it says when for these values, like the solution is nearly Kähler, when it's Kähler, of course, when it is 1. So in particular, this is nothing but saying that in this case, where it found the solution to the nearly Kähler equation, also there are many metrics, infinitely many. Okay, so now, I mean, we go to another type of equation. It's the generalization of the Killing-Yano. It's a Riemannian manifold, and it says to satisfy the conformal Killing equation if the form satisfies this equation. Here is written, I mean, this is interior multiplication by x, so the first part, the first term in here is just if this is 0, is the equation we had before. So when d star is 0, okay, we have the Killing-Yano. Okay. Okay, this is some properties of the conformal Killing. But I will show you. This is. Okay, conformal Killing are generalization of conformal Killing vectors. It's the same case as before. We had Killing vector fields and Killing-Yano equation. Okay, this is, yeah, and here says that started in the last 10 years, more or less, more systematic study. Okay, now I suppose now okay, Sasakian manifolds satisfy the conformal Killing-Yano equation. In the case of two forms, now we restrict to two forms. We saw previously that in the case of two forms, like the Killing-Yano is now named, is just like the Nearly Kähler condition in the case, and Kähler, Nearly Kähler, in the case of the structure, the endomorphism to the square being or to have an Hermitian or almost Hermitian manifold. And here, like we review a little bit, a Riemannian manifold is called Sasakian if there is a unique length Killing vector field such that the derivative, the Nabla-Chibita connection of the derivative of that one form satisfies the equation that is written there. Okay, so Sasakian manifolds, all these forms are conformal Killing-Yano forms. A Sasakian manifold is the analog, okay, in odd dimension of a Kähler manifold. And the Boyer here, I mean, they had a lot of results on Sasakian manifolds. I'm not just give it this as a motivation for the study of this kind of two forms. And so this is the relation, one of the big relation between Sasakian and Kähler. We call that Kähler manifolds, I mean, all satisfies the Killing-Yano, I mean. So we are searching for solutions. Okay, now what we did with the colleagues Barberi and Andrada in Cordoba, we searched for invariant solution of the conformal Killing-Yano equation on Lie groups equipped with left-invariant Riemannian metrics. Okay, and this is, and some general results are this kind of result when the Lie groups is compact equipped with a bi-invariant metric or two-step nilpotent. The only invariant solutions occur on the 3-dimension. They have to be 3-dimensional, the groups. Yeah, in those cases where the metric is fixed specific. In the case of 3-dimensional Lie group, we completely classified all invariant conformal Killing-Yano two forms. And we obtain families of globally defined matrix. This is already published, searching and determine which one are Sasakian. Which of the two forms are coming from a specific one form. But there are previous results, I mean, that tell us that we have to search in dimension 3 because they cannot occur in solution in other dimensions for fixed metrics. No? Oh. Okay, so what kind of restrictions do we obtain? This is just another way of writing, okay, the conformal Killing-Yano equation for two forms. So the special one form, when one has two forms that satisfies a conformal Killing-Yano equation, one has a special one form that is given, okay, we have two forms. The special one form is given by the derivative, the dual, okay, of the two form. And we, in order to obtain certain restrictions that I'll show you, we assume that these two forms, the derivative and the other derivative of the two forms, this, we assume that this is different from 0. Because if this is 0, then we have the Killing-Yano equation. And we will show, I mean, the idea is to obtain some results. And this I will explain. This is, yeah. Yeah, this is the only group. So yeah, exactly. We have a left-invariant matrix and yeah. I mean, these X, Y, and Z are left-invariant vector fields. Okay? But this means if it is solution for, these are exactly the forms of left-invariant forms, two forms, satisfying the Killing-Yano equation. Okay? They are invariant, the solutions. Okay. So this is the first important restriction that we obtain, that if one has at the Lie group level one two form or one transformation, skew transformation satisfying the conformal Killing-Yano equation, then this, the dimension is odd. The dimension is odd and other properties, okay? Then, so now is like we are searching for trying to build the Lie algebras, the Lie algebras that carry this kind of metric Lie algebras that carries this kind of two forms. Solution. So these are restrictions. This is like a first strong result. You see, if this, I don't know if this is true, okay, we have the dimension of the group is odd. Here, the special direction is, this is the special direction, okay? And then in the perpendicular is a linear isomorphism. Oh, you'll see, this is a linear isomorphism. If one has, for example, that, I don't know if this is true, that the exponential is a closed subgroup, the exponential of t times size is a closed subgroup, then we can take like the quotient, the Riemannian quotient, and then look at something like a geodesic, totally geodesic vibration. But I don't know if this happens. I mean, I don't know if this is, because this is the condition of being totally geodesic. This, okay? I don't know if this is true in general, okay? In some cases, we can do that, but... okay, so, this is, when I mention, I mean, the case of dimension 3, I mean, we prove, I mean, that these are the three-dimensional, the algebras of group carrying, this is, the whole means H. This is the Heisenberg. In here. Okay, to show in these cases when we are searching for solutions, we see that the groups not necessarily have center. For example, you see here SL2. So we have solutions, but the solution is not coming from the center. It's not, I mean, this. So this is just an observation. So, and this is the main result we have, we proved recently, is that if one has a conformal Killing-Yano tensor, okay, on a Lie group, this is always invariant because we are with left-invariant metrics, and this special vector, okay, comes from the center. Then the center has dimension 1. The center has dimension 1, and is exactly a central extension of another group, another Lie group. But what is important, I think, is the main result, is that the other Lie group carries a solution to the Killing-Yano equation. It's something like one has a Killing-Yano, invertible solution to the Killing-Yano, one takes the central extension, or that is mainly the conformal Killing are central extension of Killing-Yano. Okay, this is mainly what, but with the restriction that this element, for example, this element comes from the center. That will not be always the case. In the case of Sasakian Lie groups, this is always the case, at least in the nilpotent case, okay? But this is in the case of conformal, but with this restriction, I mean, assuming that this element comes from the center, that is case, I mean, we analyzed the case of dimension 3, then in the case that it comes from the center, then it's a central extension of a Killing-Yano. So, summing up, it's something like we have solutions that are Killing-Yano, and then central extension of some kind of extension or fibration, I mean, will give you solutions to the conformal Killing-Yano. Okay, so we are trying to see this. It's some parallel between Sasakian and Kähler, or contact, I mean, this kind of at least. I think, I mean, the best restriction we obtained, but I don't know if this holds in general, is the condition that it satisfies the conformal Killing-Yano equation, then it has to be odd dimension. And certain restriction on the special direction. So I think this will be. So from this result, I mean, we can build a lot of examples of manifolds. Why? Because we start with a low dimensional manifold, a Lie group, for example, 4 dimension, with a parallel structure, with parallel, and then take the central extension, and we will build 5-dimensional Lie groups, carrying a solution to the conformal Killing equation. And so this is a strong, to have examples of manifolds with forms satisfying this condition. Okay, I think it's all. I have some references if somebody is interested. I mean, various references, not all, of course. Okay. Okay, thank you.
So you say for any Sasakian structure you have Killing-Yano.
Yeah, all Sasakians satisfy that equation.
What about the conformal?
also define these equations, different equations. Particular cases.
More questions for Isabel? If not, let's take the speaker again.